As we begin our study of basic hydraulics, we must first recognize that fluid power is another method of transferring energy. This energy transfer is from a prime mover or input power source to an actuator or output device. This means of energy transfer, although not always the most efficient, where properly applied may provide optimum work control. Energy may be defined as the ability to do work. Work is defined as force through distance. If we move 1,000 pounds a distance of 2 feet, we have accomplished work. We measure the amount of work in foot-pounds. In our example, we have moved 1,000 pounds 2 feet or have accomplished 2,000 foot-pounds of work. Power may be defined as the rate of doing work, or work over time in seconds. If we lift 1,000 pounds 2 feet in 2 seconds, we have accomplished 1,000 units of power, or 1,000 times 2 divided by 2 seconds. To give us relative meaning for measuring power, we must convert this to horsepower, which is a unit of measuring energy. Mathematically, hydraulic horsepower is expressed as follows. Horsepower equals flow in gallons per minute times pressure in pounds per square inch divided by 1,714, a constant. In our illustration, we are lifting 10,000 pounds, this is our force, a distance of 1 foot, this is the work to be accomplished. If we lift our load in 2 seconds, we have defined a power requirement. This may be expressed as hydraulic horsepower. To lift our 10,000 pounds a distance of 1 foot in 2 seconds, we must have a required flow rate at a specific pressure, based on cylinder size and pump flow discharge. In this illustration, a 10-gallon per minute pump is required to extend the cylinder in 2 seconds. The pressure requirement to lift the 10,000 pounds is 1,500 psi, based on cylinder diameter. Based on our formula, our theoretical horsepower requirement would be 8.75. The law of conservation of energy states that energy can neither be created nor destroyed, although it can change its form. Energy in a hydraulic system that is not used for work takes the form of heat. For example, if we have 10 gallons per minute going through a relief valve, which has a pressure setting of 1,500 psi, we can calculate the energy being converted to heat. Torque is twisting force. It is also measured in foot-pounds. In this illustration, we are producing 10 foot-pounds of torque when we apply 10 pounds of force to a foot-long wrench. This same theory applies to hydraulic motors. Hydraulic motors are actuators that are rated in specific torque values at a given pressure. The twisting force, or torque, is the generated work. A motor's RPM at a given torque specifies our energy usage or horsepower requirement. This learning lab will demonstrate the effect of flow and pressure requirements on theoretical input horsepower required. Clicking on the arrows labeled GPM will increase or decrease the pump flow output, while clicking on the arrows labeled load will increase or decrease the load on the cylinder. Clicking on the extend or retract will shift the valve and operate the circuit. Observe the changes in horsepower requirements. Flow in a hydraulic system is produced from a positive displacement pump. This is different from a centrifugal pump, which is not positive displacement. There are 3 important principles that must be understood relating to flow in a hydraulic system. Principle 1. Flow makes it go. For anything to move in a hydraulic system, the actuator must be supplied with flow. This cylinder is retracted. It can extend only if there is flow into port B. Shifting the directional control valve will send flow to either extend or retract the cylinder. Principle 2. Rate of flow determines speed. Rate of flow is usually measured in gallons per minute, or GPM. GPM is determined by the pump. Changes in pump output flow will change the speed of the actuator. Principle 3. With a given flow rate, changes in actuator volume displacement will change actuator speed. With less volume to displace, the actuator will cycle faster. For example, there is less volume to displace when we retract because the cylinder rod occupies space, diminishing the volume to be displaced. Notice the difference in speed between extend and retract. In this learning lab, you will learn how flow gives us actuator speed based on a specific pump output and actuator displacement. First, click on Extend or Retract to begin flow. Use arrows to adjust pump size, GPM, and actuator size. Notice the speed of the actuator as the GPM and/or actuator is adjusted. Pressure in a hydraulic system comes from resistance to flow. To further illustrate this principle, consider the flow produced from a hydraulic pump. The pump is producing flow, not pressure. However, if we begin to restrict the flow from the pump, pressure will result. This resistance to flow is load induced from the actuator and also generated as the fluid is passed through the various conductors and components. All points of resistance, such as long runs of pipe, elbows, and various components, are cumulative in series and contribute to total system pressure. Pascal's law forms the basis for understanding the relationship between force, pressure, and area. The relationship is often expressed with the following symbol. Mathematically, we express this relationship as force is equal to pressure times area. Pressure is equal to force divided by area, and we can calculate area by dividing force by pressure.
Pascal's law is expressed as follows. Pressure applied on a confined fluid at rest is transmitted undiminished in all directions and acts with equal force on equal areas and at right angles to them. In the following illustration, we have a vessel filled with a non-compressible fluid. If 10 pounds of force is applied to a 1 square inch stopper, the result would be 10 pounds of force on every square inch of the container wall. If the bottom of the container was 20 square inches total, the resultant force would be 10 psi times 20 square inches, or 200 pounds of total force, since force equals pressure times area.
In this learning lab, you will directly see the effects of Pascal's law. By pulling down the lever, you will put equal pressure on the fluid within the system. Note the pressure gauges all read the same pressure throughout the system. Load-induced pressure is defined as pressure generated from the load or force on the actuator. The effective area of the cylinder piston is the area available for force generation. In our illustration, a 10,000-pound force gives us a load-induced pressure of 1,000 psi based on our formula. When the cylinder is extended, the required pressure to move the 10,000-pound load is 1,000 psi, less frictional forces. During retraction, the effective area is only 5 square inches. This increases the required pressure to 2,000 psi needed to retract the load. In this learning lab, we will learn that as we increase the load on a cylinder, the required pressure to maintain that load must increase. This is accomplished by stacking and unstacking the provided weights, increasing the load on the cylinder. Pressure that is not directly used to provide work may be defined as pressure drop or resistive pressure. It is the pressure required to push the fluid through the conductors to the actuator. This energy takes the form of heat. Excessive pressure drop may contribute to excessive heat buildup in the hydraulic system. This resistive pressure is accumulative and must be added to the overall system pressure requirements. In this learning lab, you will pick and place the elbows, reducers, and pipe lengths to the system. As you add these elements to the system, notice that the pressure increases. When we reach a pressure of 1000 psi, heat will be coming from all areas of the system. The study of fluid power deals with the understanding of the transmission of energy through a confined liquid. The hydraulic fluid may well be considered the most important component in a hydraulic system. It serves as a lubricant, a medium for the transfer of heat and energy, and a sealant. Let's look at some examples of these. In our example of lubrication, hydraulic fluid as a lubricant allows this block to glide with less friction and wear on the parts. In our example of heat transfer medium, the heated fluid enters and radiates its energy out and leaves the system cooler. In our example of energy transfer, hydraulic fluid will transfer energy from the input side to the output side because fluid is basically non-compressible. In our example of a sealant, the hydraulic fluid between the wall and the piston will act as a sealant because of its viscosity. Hydraulic fluid is basically non-compressible and can take the shape of any container. Consequently, it has a certain advantage in the transmission of force. This is an example where the fluid will take the shape of a container. Using a positive displacement pump, the energy from the prime mover or input source is transmitted to the actuator or output through the medium of a non-compressible fluid. As the fluid passes through the conductors and components, certain considerations must be given to ensure maximum efficiency in the transfer of energy. These considerations include the understanding and the proper application of fluid velocity and viscosity. Velocity is the distance a fluid travels per unit of time. With a fixed volume of fluid going through a conductor, the velocity of the fluid will depend upon the inside diameter of the conductor. If the diameter of a conductor is increased, the velocity of the fluid will decrease. Conversely, if the diameter of the conductor is decreased, the fluid's velocity will increase. To better illustrate this principle, we have two simple systems in which two pumps of equal displacement of 30 gallons per minute move fluid through conductors of different sizes. The displacement remains equal, while the velocity of the fluid varies with the size of the conductor. The fluid turning flywheel 2 is moving 4 times faster than the fluid turning flywheel 1 because the inside diameter of the pipe for flywheel 1 is twice the size of the inside diameter of flywheel 2. However, the flywheels turn at the same rate because the volume displacement is equal in both systems.
Viscosity is a measure of a liquid's resistance to flow. A thicker fluid has more resistance to flow and a higher viscosity. Viscosity is affected by temperature. As a hydraulic fluid's temperature increases, its viscosity or resistance to flow decreases. A viscometer, the device used to measure a liquid's viscosity, consists of a small reservoir surrounded by a water bath used to heat and maintain the liquid at a constant temperature. There is a small orifice below the reservoir through which the liquid can pass once it is heated to a specified temperature. A stopwatch is used to determine how much time it takes to fill a 60 milliliter flask. The number of seconds that it takes to fill the flask at a given temperature is the liquid's viscosity at that temperature. As illustrated, the fluid on the right has a lower viscosity than the fluid on the left.